Hi everybody, let's continue with section 4.7. Let's look at the problem. Use the compound interest formula to calculate the amount of money you would have after 1 year if you invest $1 at 100% compounded annually, monthly, quarterly, and daily. So when we look at this problem, it's a very unlikely case, but the purpose of this is to see what the amount is tending to as our n increases. So if you recall, the compound interest formula is A equals P times 1 plus R over N to the N times T. And so when we plug that in for the first part, we'll have A equals 1 times 1 plus R, which is going to be 1 over N, annually is 1, to the N times T, or 1 times 1. When we do the math on this, we'll get 2 to the 1, so our answer is 2. When we look at, let's do quarterly first, so we can just kind of stay in order here. So when n is 4, we're going to have A equals 1 times 1 plus 1 over 4 to the 4 times 1. So we'll get 5/4 and then 5/4 to the 4th. I'll need to use my calculator. And so I get 2.4, and I'm going to write some more decimals. 1406. And when our interest is compounded monthly, n is 12. So A is going to equal P, which is 1, times 1 plus R, which is 1 over 12, to the 12 times 1. We'll get 13 over 12 to the 12. And again, using my calculator, I come out with 2.613035. And just peeking at part E, we want to notice what's happening to our answers as n is increasing. So when we look at part D, daily, we'll have n is 365, which means we'll have 1 over 1 divided by 365 to the 365. We'll get 366 over 365 to the 365, which comes out to approximately 2.17. Oops, no, I have that backwards. 2.71457. And hopefully you're starting to recognize that this is going to something. Maybe just to try one more example, let's look at when n is 1,000. So that means A would equal 1 times 1 plus 1 over 1,000 to the 1,000 times 1. This would be 365 times 1. So then you'll get 1,001 over 1,000 to the 1,000. And this is approximately 2.7169239. So what are you noticing as you increase n? Hopefully you're realizing that this approaches E. So what we can realize from all this is the act of compounding without bound is expressed as continuous bounding. And so recall that E was approximately 2.718281828459, and based on this example, what we saw is that e is equal to the limit as x goes to infinity of 1 plus 1 over x to the x. So this is why I wanted to capture such weird constraints for our compound interest example. And so here I just replace n with x, so just using x instead of n. And this idea of the limit is saying as x is getting larger and larger and larger, right? Because for this example, we saw that it was 2. When it was quarterly, it was 2.44. And then when it was monthly, it was 2.2. No, I looked at the wrong spot. So this was 2.7169. And when we did daily, we got 2.714567.4. So what that's telling us, right, is the value for n is getting larger. For n is 1, n is 4, n is 12, n was 365. When we did n is 1,000, as we evaluated this answer became closer and closer to e, so much so that we can say that it is e. So in the limit, this idea of we can always get a little bit closer to infinity, but when we get large enough, we're saying that this expression is when evaluated for really large values of x, it is infinity. So hopefully you found, oh, one more thing. So then what this is telling us is that because we were compounding without bound, meaning that it's continuous, compounding continuously, we're saying that a equals p e to the r times t. So this part, that was the same as this. Since it goes to e, we're replacing it because n is so large that we're compounding continuously. So when you see the words compounded continuously, we use this formula. If you see that the phrasing of the problem says compounding monthly, then you're going to use the other formula. All right, so I hope you found this helpful. See you in the next video.